Hey everybody, it's Rippy back again. Welcome back. We're going to talk about surface areas of a surface of revolution today. It's out of 10.2 in the text. So just to give you a brief idea what we're talking about, let's say that I have a function, and like before, let's just let this guy be f of x on a closed interval from a to b. Keep it simple. And what we're going to do is we're going to wrap this guy through 360 degrees, but instead of taking the volume that creates when I wrap that thing through 360 degrees, we're just worried about the surface area. Now, you can hopefully at this point, this is going to be a nightmare, but you can visualize, it's kind of like a bell shape. Hey, that's pretty good. So this guy goes through 360 and through 360. And what we end up with is a volume, but I want to know the surface area. So instead of volume, which volume would be pretty easy, right? We know how that works. The volume would simply be pi times the integral from a to b of f of x squared dx, which we've known. I don't care about the volume though. I want to know what the surface area is. Now, to be able to do the surface area, excuse me, to be able to find the surface area, I need to start with an idea called a frustum, which is kind of interesting. It's awful to say, but what a frustum is let's say that, like we've done before with things like arc length, if I take just this little slice right here, okay, this little slice of black right here, that's going to approximate the curve of f of f on some sub-interval. When I wrap that thing through 360 degrees, what I end up with is a part of a cone with the top cut off. Now I'm botching this horribly, so what I'm going to do is I'm going to show you what it looks like. This is a frustum, all right? Now, excuse me, a frustum has an equation which we learned back in geometry, or you should have. And the area of a frustum, so I'm going to go a sub little f. Oh, by the way, let's write out what that is. That's frustum. All right, that guy. The area of a frustum is given as 2 pi r times the length of the side. So this guy right here would be the length. And r is a little bit tricky. So what we do with r is we hedge our bets a bit. We're going, whoops, what did I do? Let's do this guy, sorry. All right, what I do is I take the sum of the two radii and I divide by 2. So if this was r1 and this was r2, then this would turn into 2 pi times r1 plus r2. Whoops, not r squared. What are you doing, Ripley? Plus r2 over 2. Take the average of that over 2. And then I multiply that times the length of that side. All right, so that's the formula. So let's keep that in mind here for just a sec, because now is where it gets fun. Once we've done this, we've done the heavy lifting. So what we're going to do is, let's get back to black. We're going to get over here. What we're going to do is, if you think about how integrals work, or if you remember, excuse me, you're going to have a bunch of these little frustums, and we're going to add them all up. But if you think about it, what are the frustums supposed to represent? Well, they're supposed to represent the length of the arc, right? And we know arc length. So if I want to know, I pounded this into you, hopefully, the arc length of a curve is simply the integral from a to b of the square root of 1 plus dy over dx squared. Dx, if it's a function of x, it's equal to the integral of from a to b of 1 plus dx over dy squared, the square root of that, dy if it's a function of y. And then lastly, if it's a parametric, then it's going to be a to b of the square root of dy over dt. Just a quick little review, squared. Nothing wrong with that, right? Plus dx over dt squared dt. And this is for x between a and b. This is for y between a and b. This is for a function of y. Excuse me. And then this guy is for t between a and b if it's parametric. So if I have the equations for arc length, which we've already used, and I have this new equation for the area of a frustum, such a strange word, which is already created, if you think about it, by revolving a line around an axis, which just gives you part of the cone, then I can combine the two to get the overall surface area, which is really simple. So I've got, let's take the surface area of a solid that is wrapped around the x-axis, and therefore we have a function of x. It's simply the integral from a to b of 2 pi times, now what would this r thing be if I'm going from the x-axis up to the function? And these l's, these lengths of the side, are shrinking to 0, right? That is created because I've got the integral from a to b. If the length of this side of the frustum shrinks to 0, then we only have one radius. We no longer have to take the average of two radiuses, radii, and that radius is simply f of x. So I can just go 2 pi times f of x times the square root of 1 plus, not plus plus, I guess that's redundant, but still, in the interest of being accurate, notation, dy over dx squared dx. And voila. Next, this again is for a less than or equal to x less than or equal to b. If I've got a function around, or excuse me, a function of y, it becomes the integral from a to b of 2 pi times f of y times the square root of 1 plus dx over dy squared dy, and this is for y between a and b. And last but not least, if I've got a parametric. Now you got to be careful with parametrics, right? I'm going to kind of just make some scratchies over here. If I've got a parametric that does something like this, right, and I want to go from a to b, like I really have to have a discussion with myself about what truly is the surface area of this thing. All right, so we're going to completely oversimplify this, though. We're going to say that we don't have any hoopty-doopty-loopties, all right? And we're simply going to, this is for further discussion about what happens when this thing wraps around itself, all right? We can talk about that a little bit in class, or we can discover it in a project. So needless to say, I've got the integral from a to b of 2 pi. Now, what do I use for this radius? Well, because it's a parametric, it's a function of t, I can sort of arbitrarily choose like what I'm going around as far as the surface area, right? So in this case, we're going around the x-axis. So this guy is going to be, I can't write f of x, right? Because my functions, I have two functions, both of which are of t. But all I'm going to do is I'm going to do y of t, because that's the vertical distance between the x-axis and the parametric equation, right? If I were going around a y-axis, then what would it be? Well, you can think about that. It's super simple to deal with. So this is times the square root of, what am I doing? dy over dt squared plus dx over dt squared. This is dt, and this is for t between a and b. Isn't it delightful how, I just said delightful, isn't it delightful how once you start building all this knowledge of calculus, a lot of the equations, a lot of the ideas, a lot of what we do, the mechanisms and the computations just fall out. And then we're happy because we got all the information that we need. All right, hope this was helpful. Again, this is out of 10.2. This is going to be helpful for down the road as we work our way through the vector calculus. Thanks for listening to you, and I'll see you tomorrow in class. Bye-bye.